You know, magnetism is one of those things that's just everywhere. It's the invisible force holding a note to your fridge, for sure, but it's also the force that holds entire galaxies together. It operates on every scale you can possibly imagine. So today, let's pull back the curtain on this fundamental force that literally shapes our universe.
We've all played with magnets, right? But have you ever stopped to think about this simple question? If you take a regular bar magnet and you snap it in two, you'd think, logically, you'd get a North Pole piece and a South Pole piece. But that's not what happens at all, is it?
Nope. Instead, what you actually get is two brand new smaller magnets, and each one has its own North and South Pole. You can keep breaking it smaller and smaller, and you will never, ever get a lonely North Pole or an isolated South Pole. This little experiment hints at a really profound, unbreakable rule of the universe. So what's going on? Why does this happen every single time? Well, to get the answer, we have to look past the physical magnet itself and dive into the invisible world of its magnetic field. So let's do it. Let's peel back that curtain. Okay, so to solve the mystery of our broken magnet, we first need to get a handle on the basic rules that govern all magnetic fields. You can think of these as the fundamental laws of magnetic behavior, and they never, ever get broken. Now, the most important rule, the one that's the key to this whole puzzle, is right at the top. Magnetic field lines are always continuous, closed loops. They flow out of the North Pole, they curve around into the South Pole, and then they continue right on through the inside of the magnet. This one property changes everything. And this is where we see just how different magnetism is. Take electric fields. They have a very clear beginning and a very clear end. They burst out from positive charges and they stop on negative ones. You can totally have an isolated positive charge. But magnetic field lines? They have no beginning, no end. They just loop infinitely. Now, this whole no endpoints rule has a pretty official name, Gauss's law for magnetism. But in plain English, all it really means is that for any closed shape you can possibly imagine, every magnetic field line that goes in must also come out. There's no source and there's no sink inside. So the huge takeaway here is that isolated magnetic poles, what we might call monopoles, they just don't seem to exist in our universe.
All right, so we know magnetic poles always come in pairs because their field lines are loops. But why are they loops? To answer that, we have to go from this big picture view all the way down to the atomic level.
The big breakthrough came from a guy named Ampere. He had this revolutionary idea. He proposed that all magnetism isn't from some kind of special magnetic substance. It's actually a side effect of something we're all familiar with, moving electric charges, or, as he put it, circulating currents. And this idea goes all the way down to the atom. So check this out. First, you've got electrons orbiting a nucleus. Well, as step 2 shows, that moving electron is, by definition, a tiny little loop of electric current. And we know from step 3 that any current, any moving charge, generates a magnetic field. So what's the result? As you see in step 4, every single atom can act like a teeny tiny little magnet, a dipole, with its own north and south pole.
And boom, there's our answer. A permanent magnet isn't some magical object. It's just a chunk of material where trillions and trillions of these tiny atomic magnets have all lined up and are pointing in the same direction. So when you snap it in half, you're not splitting north from south. You're just creating two smaller, but still perfectly aligned armies of atomic magnets.
Okay, so now that we get the secret sauce, we can start to understand why different materials react to magnets so differently. I mean, not everything sticks to a magnet like iron does, right?
We can basically sort all materials into 3 big buckets. First, you have diamagnetic stuff, which is actually weakly repelled by magnets. Then there are paramagnetic materials, which are weakly attracted. And finally, you have the heavy hitters, the ferromagnetic materials, like iron, which have these pre-aligned regions and are strongly attracted.
Now, diamagnetism is super interesting because it's actually in everything. Water, copper, even you and me. When you bring a magnet close, it induces a tiny current in the atoms that creates an opposing field. It basically pushes away, very, very weakly. It's usually so faint that other stronger effects just completely overpower it.
Paramagnetic materials, like aluminum, are a bit different. Their atoms are already permanent little magnets. But normally, all that thermal energy has them jiggling around, pointing in completely random directions, so their magnetic effects just cancel each other out. But an external field can coax some of them to line up, and that creates a weak attraction.
And then we have the superstars of magnetism, ferromagnetic materials like iron. What makes them so special is this idea of domains. Inside the material, there are these huge regions. We're talking billions of atoms that have already decided to align with each other all on their own. It's like they form little magnetic neighborhoods that are all in sync.
So, making a permanent magnet is really just about getting all these domains to work together as a team. As you can see, in a normal piece of iron, the domains are all pointing in random directions. But then, you apply a really strong external magnetic field. This causes the domains that are already kind of lined up with the field to grow, while the others rotate to match. In some materials, this new unified alignment gets locked in, and voila, you've got a permanent magnet.
All right, we've covered the basics. We know how normal magnets work. Now let's look at the absolute extremes, the outer limits, where materials start doing truly extraordinary things with magnetism.
I want you to meet superconductors. When you cool certain metals way down to incredibly low temperatures, something amazing happens. Not only do they conduct electricity with literally zero resistance, they also become perfect diamagnets. They become the ultimate magnetic repellers.
Physicists have a way of measuring this magnetic response. It's a number called susceptibility. For a superconductor, that number is exactly -1. What that means is it doesn't just resist a magnetic field a little bit. It generates its own internal field that is perfectly equal and opposite, achieving total absolute cancellation.
And this perfect opposition leads to a stunning visual effect called the Meissner effect. A superconductor doesn't just weaken a magnetic field, it completely kicks it out. The magnetic field lines are literally forced to flow around the material, as if it were a rock in a stream. They cannot pass through.
Which brings us to a final incredible question. If a material can perfectly, actively push away a magnetic field, what does that let us do? Well, it means you can use one magnet to repel it so perfectly, so stably, that it just floats. This is the magic behind magnetic levitation, the principle that could power everything from frictionless bearings to mind-blowingly fast trains. The unseen force finally made visible. Makes you wonder, what other invisible forces are out there, just waiting for the right material to reveal themselves?